This is question 1 from the third CSAT sample paper. In this question we're asked to sketch mod x to the n plus mod y to the n equals 1 for n in the set 1, 2 and 1000. So if you want to have a go at this question yourself, pause the video now. Okay, so we have three things to do to sketch for 1, 2 and 1000, and I'll call these A, B and C, so let's start off with A. So in the case A, if we're putting something to the power 1, it's the same as just leaving it on its own, so we have mod x plus mod y equals 1. And there's a couple of ways you can do this. Let's look at one first. So one thing you might try to do is to make y the subject. So write mod y equals 1 minus mod x, and then you're kind of stuck because you've got mod y equals, and there are a couple of ways to turn this into y equals. So for instance, you can think about the cases where y is positive or negative, and write separate equations for those. You can also just think about how to sketch a graph mod y as a function of x. So let's sketch this. And if you're sketching mod y equals something, the easiest way is to start off with thinking what y equals f of x looks like. So we'll think about that in a second. And then what does it have to look like for mod y to be equal to this? Well, there's a couple of rules. So firstly, we only want to keep the positive bit. So where f is positive, we want to keep that bit, because those are also going to be solutions of this. But if mod is negative, then there's no value of y such that mod of it is going to be negative. So these bits just won't feature on our mod graph. And we also want to reflect in the x-axis, and that's because if there's a positive value of y that makes this work, so say f of, let's say x is 1 here, let's say f of 1 is 3, and this is at the point y is 3, x is 1. Then if we choose y as minus 3, so down here, that would also be a solution to this because mod of minus 3 is the same as mod of 3. So that's just the same as saying that the graph of, like when we draw the graph of mod x, it's symmetric in the y-axis. If we're drawing something with mod y, it's going to be symmetric in the x-axis. So in this particular case, we'd copy this bit and this bit and this bit and then reflect them. So we get something like this. Here's this bit in the middle, and this bit. And then we reflect, and often what happens is you get kind of points where the two meet. So in this case, we want to first think about sketching the right-hand side, just as y equals this. So if we have, to start with thinking about what this looks like, if we have mod x, we know what that looks like. And this is the same as minus mod x plus 1. That's often the easiest way to think about it when something's been taken away. So to do minus mod x, we just flip it so it's underneath the x-axis, so it looks like this. Then if we're adding 1, we just move this up by 1. So what does that look like? Well, if we move it up, the point goes to 1, and then because these lines are at 45 degrees, we get crossing at minus 1 and 1. And then we said we want to keep the positive bit and reflect, so we're just going to get a diamond shape like this. So this is the graph we're looking for. So I'll just quickly mention another way you can think about mod graphs. If you think about mod x plus mod y equals 1, well, what are the general features of this? One is that it's symmetric in the x and y axes, because x and minus x are treated the same. They give the same answer, the same for y and minus y. And also, we know what happens when x and y are positive. If x and y are positive, then the modulus sign doesn't make a difference. So basically, for x and y both positive, this would just be the same as x plus y equals 1. And together, those give us a way of approaching the question, because this tells us what happens in the top right quadrant. So we could sketch x plus y equals 1 there, and then we can reflect it in the axes because we know it's symmetric in the axes. So let's try doing that. So what does x plus y equals 1 look like? Well, that's the same as y equals 1 minus x, and that's just a straight line passing through 1 and 1. And we're only drawing this in the top right quadrant. So you could also find separate equations for these quadrants. Like for instance, if we were here where x is negative, then mod x would be the same as minus x, so we'd have y as 1 plus x instead. And that would look like this. But the other way is just to reflect in the axes. So if we reflect in this axis, we get this line, and then we can reflect that in the x-axis. And so we get back our diamond that we saw before. Okay, next up is when n is 2, so mod x squared plus mod y squared equals 1. If you want to have a go at this yourself, pause the video now. Okay, the thing to notice here is that mod x squared is just the same as x squared because it if x is positive, we have positive x squared. If x is negative, we have negative x squared. And minus squared is the same as plus squared, so it doesn't make any difference. So this is the same as x squared plus y squared equals 1. And you should immediately recognise that this is just the equation of the unit circle, so centre 0, radius 1. Okay, so that wasn't too difficult. Let's now, we'll put in what we got for A as well, just so we can compare, and now we'll think about C, which is more difficult. So in C, we were asked to do it for n is 1,000. So we're sketching x to the 1,000 plus y to the 1,000 is 1, again because mod x to the 1,000, because it's an even power, it's just the same as x to the 1,000. So looking at what happened for n is 1 and n is 2, if you want to have a go at sketching this, pause the video now. Okay, so let's think about some common properties of these two. One is that they're symmetric in the axes, and that's basically because mod x is symmetric in the y-axis, mod y is symmetric in the x-axis. Okay, when we square, we don't need the mods, but that just means that if we square, it's still symmetric in the axes. And this is also going to be symmetric in the axes for the same reason. And we also see it goes through these 4 points, which also isn't a coincidence. So what do we know about this? We know these points, so plus or minus 1 on the y-axis and plus or minus 1 on the x-axis are going to be on the curve. And that's because, well, if we make one of these 1, then the other has to be 0, because we're adding two positive things to make 1. And we know that it's symmetric. And because we're adding two positive things to make 1, that means that neither of these things can be bigger than 1 either. So if x to the 1,000 was 2, then this would have to be minus 1, and that can't happen because it's an even power. And even if it was an odd power, because it would be mod to an odd power, so it would be positive. So that means whatever happens, x and y are going to be between minus 1 and 1, which is what happens for both of these. They're kind of stuck in this box here. So that tells us something about the shape. It's going to look something like this. So obviously this is a weird shape that won't actually happen. But it's going to be symmetric, it's going to go through these points, it's going to be stuck in this box. So all we need to think about now is the shape. What's the shape? And I've drawn a different shape in each quadrant, and then we could imagine reflecting each of them around. So it could be a weird bumpy shape like this, for all we know. Or if we think about the first two cases, they were quite simple. And, okay, a straight line has already happened, it's unlikely to happen again at x equals 1,000. That happened for n equals 1. But the curve could instead sort of bulge out or bulge in towards the axis, so we have to decide which is going to happen. In fact, if we look at what happened when we increased the power from 1 the first time, it bulged out. So we can kind of expect it's going to bulge out even more. In which case the question might be how much and how do we draw it. So now let's have a look at how we decide on the shape. Okay, so here's our equation, and I think one thing it's important to look at is the fact that x and y are always between minus 1 and 1, which we said before. And why is that important? Well, 1,000 is just an arbitrary number, but they chose it to be large, that's the point, it's a large number. And if we put something that's between minus 1 and 1 to a large power, it gets smaller and smaller and closer to 0. And it's going to be very close to 0 because there's such a large power involved. The only exceptions are at minus 1 and 1 when these things are actually going to be equal to 1. Or very, very close when they're going to be closer to 1. And at x and y is equal to 0, then we get exactly 0. And to think about what difference that makes to the shape, I think it's helpful to look at what happens for polynomials in increasing even powers. So y equals x squared, we know what that looks like. And then if we think about increasing the power to x to the 4, when x is between minus 1 and 1, because we're putting it to a larger power, it's smaller, so it's closer to the x-axis, it's flatter here. Except that at minus 1 and 1, it has to always pass through y equals 1. And therefore it has to increase very quickly to get up to there, because it's got to be so small here. So it's small everywhere until we get very close to 1 when it starts increasing more to here. And then after that point it grows much more quickly. And then if we think about x to the 6, well, it's going to be the same, just even square, because it's even smaller in here, and then it has to increase even faster to get up to here. And if we imagined putting it to the power 1000, it would be very squared off compared to this. It would be basically like the bottom of an infinite rectangle. We come straight down and then straight across and then straight up again. So you can kind of imagine what the shape's going to look like, but let's explain precisely why. So unless x is very close to 1 or very close to minus 1, x to the 1000 is very close to 0, and that means that y to the 1000 has to be very close to 1 from here, and that means that y has to be very close to 1 or minus 1. So unless x is very close to 1 or minus 1, y has to be very close to 1 or minus 1. So that means we basically get, for alternatives, x is somewhere in the middle and y is close to 1 or minus 1, or y is somewhere in the middle and x is close to 1 or minus 1. So what does that mean? Well, let's draw our axes. We know we're going to be in this box somewhere. And if we think about what happens just for positive x and positive y, so in this quadrant, if x is anywhere in here, then x to the 1000 is very close to 0, so y has to be very close to 1. Until we get to here where x is very close to 1. And then y could be basically anything except 1, because if we put it to a large power, it would be close to 0 anyway. So y could be basically anything, almost anything up here. So that means what we're going to get is a kind of corner of a square. Another way of thinking about it is just to think about the x's. So we know when x isn't very close to 1, we get y very close to 1. So we get almost a straight line. It's decreasing ever so slightly up to this point where it suddenly has to decrease much more sharply to get down to 1. But up to this point, we can imagine, because x and y are basically, they have the same role in the equation, we could swap x and y and it would be the same equation. That means our graph has to be symmetric swapping the x and y axes, or it's symmetric in the line y equals x. So then we could reflect this line in the line y equals x, and it would just become this line. So that's again why we get this squared off shape. And then we know it's symmetric in the axes, and that means we can complete it into the other quadrants and we get this square shape. So that's what they're looking for this part.